It's September 1st, 2020. What I'm doing here is a little experiment to see how good of a heat conductor regular structural carbon fiber is. The tech ingredients guy mentioned that carbon is a much better conductor than even silver. So instead of trying to make the next prototype helmet, which will have the LEDs integrated into the helmet shell instead of in a separate unit hanging out front, I could use this. So what I've done here is packed a bunch of the fibers all pointing in the same direction, so the heat does not have to get through molecules of epoxy to get to the carbon fiber. It can go straight from here through the fibers to this, and if it's really that effective, this should be significantly faster at conducting the heat than the tech ingredients heat transfer epoxy. I'm thinking that it's not going to be that fantastic. Maybe better than Arctic Silver or the tech ingredients stuff, but not even close, I'm thinking, to any metal, aluminum or copper or anything like that. So let's test that out. Let me put the cover on. Oh, looks like I've accidentally touched that, so it's got a little head start here. Let's see what happens. Gotta get it hot, but not so hot that it's melting the plastic. That's pretty hot. Yeah, that's pretty hot. This is boring. Let me get some music going. Okay. Metal Church. Fake healer. Doesn't look like it's any better. It's not even catching up yet. Oh, maybe I should heat it up. Ow! It's hot. I'll put a link to this song in the description. Ouch. Okay. It's actually doing pretty good here. Nothing like a metal, but it's beating the tech ingredients clearly. Yeah. Huh. Well, definitely more impressive than the Arctic silver. Heat transfer is actually a measure of speed. If you had a perfect conductor, such as liquid helium, if you heated up one little spot, and let's say you had a 1,000-gallon tank of liquid helium, and you took this soldering iron and touched it on one spot on that tank, the entire mass of the liquid helium the temperature would rise a little bit, because it's so huge. It would just don't go up a little bit, but it would be the absolute same temperature for the entire tank. It wouldn't be a hot spot where the soldering iron touched it. So the numbers for the measure of heat conduction are probably kind of deceptive or hard to understand. That I think the proper perspective would be a percentage of perfection. So silver being at something like 98 or 99 would be a percentage of perfection, and then you'd see right there, okay, even though diamond or carbon nanotubes are on the tech ingredients thing, he says silver is something like 430, and then diamond comes in at like 10,000, and nanotubes are like 30,000. It's not that they are 80 times or whatever times better at conducting heat than silver. It's just that they're that much closer to perfection than silver is. Now look at it, it's already nearly 10 degrees hotter. Let's keep the heat going here. So by going from silver to diamond powder and carbon nanotubes, I think that's why it didn't do as well as the Arctic silver on my little test here in the last video, is that the difference between copper and silver is greater than the difference between silver and the carbons. It's something like 4% better, I think, than copper. So that's like 100 times more than 100 or 10? I don't know. Some multiple times better than at conducting heat than copper is, than carbon is at conducting heat than silver is. And I think the correct way to think of it is speed, that it's a percentage of speed of conducting heat. That if you had a perfect conductor from here to here, as soon as the soldering iron touches here and makes this, let's say 150 degrees, it's going to be 150 degrees instantly over here also. And then with metals like silver or copper or aluminum's like half as fast as silver. It would be a lot faster than this. So let's I've actually set this up to do that test also. So obviously we've got a decisive improvement that the heat goes through the carbon fibers, because I don't know if I mentioned this yet, but the heat, all the fibers are going the same way, so the heat doesn't have to jump through or squeeze through or crawl through a molecule of epoxy to get to the next molecule of carbon fiber. It's all fibers going the same way, so that's why it's so much better than this. Not that this is important for a let's say a heat sink for a computer processor, because on that you just got such a thin layer there that the difference between one thing and another is going to be next to nothing. Whereas here you got 7/8 of an inch where it has to go through all these different transitions from a molecule of epoxy to a molecule of copper or diamond or carbon nanotube, and then from that it'll jump through that to the next molecule of epoxy, and then has to crawl through that. So that's why this is doing better than that, because it doesn't have to do that. So let's see, I've got this piece of aluminum here on this ordinary run-of-the-mill heat transfer paste, and this song is about the sinking of the Titanic. It's off the St. Metal Church album. I think it's the first one with the new singer in it. I forgot his name, sorry man, forgot your name. But oh yeah, the album's called The Blessing in Disguise. Alright. Definitely not an ideal contact between here and here and here and here. Not ideal, but I think the solid aluminum bar from here to here is going to drastically outperform this. That's my bet. This Alright. Yeah, this one's a little ahead of that. Doesn't matter right now. I'm going to put a little solder on this to get a better contact with the bar. Ha! Look at that. Woo! I win the bet. Yeah. I'm kind of thinking that But if you took a bunch of very thin copper wires instead of these carbon fibers and packed them in there with epoxy, that it would be even faster than this. Because copper's like twice as good as aluminum. I guess that would be the next video. Another aspect of this test is that the side that's best gets a kind of a double advantage over the thing that doesn't conduct heat as fast as fast. So it's, you know, it's pulling the heat this way instead of, and then whatever would have gone that way if they were both equal doesn't. It's almost like an election where if both candidates are at 50% and one of them gets to 51%, the other guy goes down to 49, so that 1% gets him 2% above his opponent. Kind of like that. Alright, well, that's pretty conclusive.